Hello students, welcome to the 46th lecture on particle physics. And in the 45th lecture, we were talking about the suppressed decay of strange particles into non-strange particle like lambda decay, kaon decay. And in comparison to that, the decay of neutron, decay of pion, etc. What I had told you that to start with, we had U and D quarks as the doublet and strange quark as the isosinglet, while in the lepton sector we had neutrino and electron as the doublet, as well as this for the second generation of lepton we had nu mu and mu minus as the doublet. Initially it was thought that the weak interaction vortex for nu E interaction, if the interaction strength is represented by GW for an exchange of W boson, similarly that should be for U and D quark W exchange. It can be nu E bar E plus, it can be D converting into U, etc. But what was observed that not only you have conversion of U to D or D to U or U bar to D bar or D bar to U bar, you have also kaon decay and lambda decay where S is getting converted into U or U is getting converted into S. But the processes where there is a conversion of S to U or S bar to U bar or U to S or U bar to S bar, this is suppressed in comparison to the case where you have the conversion of U to D or vice versa, or U bar to D bar and vice versa. Now, this was explained phenomenologically by introducing a mixing angle that we call by the name Cabibbo mixing angle, and it was found that the decay rate for kaon upon the decay rate of pion into a muon and an antineutrino in the final state, if that is equal to tan square theta c, where the vortex for the U to D conversion, instead of GW, we are taking it to be GW cosine theta c, and for U to S conversion or vice versa, if it is treated as GW sine theta c, that means at the matrix element level, we have GW sine theta c, then decay rate is the transition matrix element square. Therefore, this will be GW square sine square theta c upon GW square cos square theta c, and that should be tan square theta c. Now, phenomenologically, that means we had the experimental numbers. We tried to fit that the best possible value for the ratio comes when theta c is around 13 degrees. And this is what we call by the name Cabibbo mixing angle. Now, with this theta c equal to 13 degree, then we are able to explain K plus decaying into mu plus nu mu and upon pi plus decaying into mu plus nu mu, or a lambda decaying into P plus E minus nu E bar upon a neutron decaying into P plus E minus nu E bar. Everywhere this was tan square theta c, besides the mass factor that has to be different, because here we have kaon mass, here we have pion mass, or here we have lambda mass, and here we have a neutron mass. That will be different. That means the phase space factor will be different. But besides that, it is proportional to tan square theta c. And experimental results can be well understood for this ratio if we take theta c to be equal to 13.1 degree. Then Cabibbo introduced the idea of quark mixing, where it was hypothesized that the D and S quarks participate in the weak interaction via the linear combination D prime is equal to D cos theta c plus S sin theta c. Therefore, the weak doublet in the quark sector is not UD, but it is UD prime. And then we have not S, but S prime as an isosinglet. Therefore, we had u d prime as the doublet in the weak sector and s prime as the singlet for the strange quark. And this s prime is minus d sine theta c plus s cos theta c, such that d prime s prime is cos theta c sin theta c minus sin theta c cosine theta c ds. You can get d prime is, and this you can see is a unitary matrix, and therefore if that means theta c is 0, d prime is nothing but d and s prime is nothing but s, but this value is 13.1 degree. This has been phenomenologically the best possible value that we fitted was 13.1 degree for theta c. Now then that means that if you are talking about u and d vortex, it is not d but it is d prime, and this vortex is gw, then this d prime is d cosine theta c plus s sine theta c, such that gud, if we are talking about u to d transition or d to u transition, then it is gud gw cosine theta c, and then it is allowing us to have u to s transition or s to u transition by defining the vortex as gw sine theta c. Therefore, this will be true even for d to u conversion, where suppose this is emitting a w minus, or this will be also true for a u bar emitting a w minus and getting converted into a d bar, or a d bar emitting a w plus and getting converted into a u bar. And as you can see, these are antiparticles, therefore arrows are in the opposite direction, and incoming u bar quark is represented by an outward arrow from the vortex, while outgoing d bar quark is represented by an inward arrow. And what this charge is minus 2 by third, and this charge is plus 1 by third, and that is what we are writing here, that it is possible only when a w minus will be exchanged. For all these cases, whether it is d to u conversion or u to d conversion, as in the middle figure we have, or d bar to u bar conversion, everywhere the vortex should be, instead of gw, it should be gw cos theta c, and that means this will be gw cos 13.1, and this means this is less than gw. Okay, therefore the important point is that it is with a reduced strength. Now since sin square theta c plus cos square theta c is 1, that means where that reduced strength is going, that is going here, which is allowing a transition of u to s or s to u, or u bar to s bar or s bar to u bar. And that is why the extreme right, on the extreme right hand side, we are finding that u to s transition is taking place. A u quark is emitting a w plus and it is getting converted into s quark, or an s quark emitting a w minus, it is getting converted into a u quark, or a u bar quark, arrow should be outward, u bar quark, an incoming u bar quark is emitting a w minus and it is getting converted into an outgoing d bar quark, s bar quark. Everywhere this will be s bar, and here it will be an incoming s bar quark is emitting a w plus and getting converted into a u bar quark. Therefore, this is u is emitting a w plus getting converted into a strange quark, s is emitting a w minus getting converted into u quark, or u bar is emitting a w minus getting converted into s bar, or s bar is emitting a w plus and getting converted into u bar. For all these vortices, the strength of the vortex will be gw sine theta c. So therefore, this was the modification suggested by Cabibbo, that the weak quark doublet is UD prime instead of UD, which takes part in the strong interaction. Therefore, weak doublet is UD prime while strong doublet is UD. Now, let us come with this concept. Let us come to the GIM mechanism. Remember, on the last turn, we have discussed the case that though K plus decays to mu plus nu mu, but KL0 does not decay to mu plus mu minus. And similarly, we gave example of various decay rates, decay of the particles, which have not been observed in nature. And this was not well understood, that why it is happening. And to understand this case, that flavor changing neutral current has not been observed, that means transition of D to S or S to D, or such example has not been observed. To understand this, GIM gave a mechanism, and GIM mechanism is after the name of three scientists, Glashoy, Illiopoulos, and Mayani. And this, to understand GIM mechanism, which is a very important concept in particle physics, because this led to the introduction of charm quark. And after this was introduced in 1970, and therefore we had UD, and in the weak case it was UD prime. Similarly, GIM introduced a charm quark, and the doublet was CS prime. Therefore, a strange quark, which was isosinglet, after the introduction of charm quark, it also became a member along with the charm quark. This charge is 2 by 3, this charge is 2 by 3, and this D prime is, remember, D cos theta W plus S sin theta W, and S prime is minus D sin theta W plus S cos theta W. Therefore, this charm quark was introduced by GIM in order to understand flavor changing neutral current, why we don't observe it, why we don't have such type of transition between D and S quark, or D bar S bar, or SD or S bar D bar, etc. Flavor changing neutral currents, they have not been neutral current, because this is minus 1 by 3 charge, this has got minus 1 by 3 charge. Therefore, the exchange that is possible is only via Z0, while U to D, U to S, D to U, D to S, S to U, that is only possible via W exchange, charge exchange, W plus or W minus. While here we are talking about D to S transition, or S to D transition, D bar to S bar transition, or S bar to D bar transition, and this is not changing charge. That means charge is not getting changed, but flavor is getting changed. D flavor to strange flavor, D quark to S quark, or S quark to D quark, flavor changing neutral current, because this exchange is only possible when there is the exchange particle is a neutral particle, and that is a Z0 particle. Flavor changing neutral current has not been observed. To explain this, GIM mechanism came, and that led to the mechanism led to the introduction of a fourth flavor of quark, charm quark. Remember, the U up quark, down quark, and strange quark, those were there when Gell-Mann and Niemann gave the eightfold way, and to explain that, Gell-Mann and Zug independently, they came out with the idea of quark flavors U, D, and S. Therefore, those concepts were from the isotopic spin and the explanation for the eightfold way, or decuplate, or nonate, etc. Therefore, that was derived from the strong interaction examples. But here we are introducing a new quark by looking at a process which is a weakly interacting process. Therefore, the charm quark was coined by GIM in 1970, and in 1974 experimentally it was observed. Therefore, the 1964 development of Gell-Mann et etc. and other people that gave the quark model, and the quark model after UDNS was moving with a very slow pace because nobody was able to observe an isolated quark, number one. Number two, only there were three quarks while four leptons were there. Therefore, everything was moving at a very slow pace. Then came in 1970 the GIM mechanism, which introduced the charm quark, and at SLAC and BNL simultaneously in 1974. SLAC stands for Stanford Linear Accelerator Center, and Brookhaven stands for BNL stands for Brookhaven National Laboratory, both in United States. Both independently experiments were performed at SLAC as well as at BNL, and a new particle was observed. This new particle turned out to be a meson, and this was a heavy meson in comparison to the mesons which were known at that time, and this could only be explained if that meson is made up of a CC bar quark. Therefore, and this discovery was so important. These two discoveries were reported in a paper that is known by the name Physical Review Letters. Physical Review Letter is a very celebrated journal in the field of physics. This is published by American Physical Society, and in the same volume, in the back-to-back pages, these two experimental reports were published, and this revolutionized the concept of quarks and gave a rapid thrust to the field of particle physics. That is why in the November volume of PRL, these two results were published. That is why this discovery is known by the name November Revolution. And here we are going to talk about a concept which was given in 1970. Experimentally, we observed a meson in 1974, and for the discovery of that J and psi meson, that is known by the name J by psi, because one fellow gave the name J and another fellow gave the name psi, turned out to be the same particle, and that is why we call by the name J by psi. This J by psi, which turned out to be made up of a CC bar charm and anti-charm quark, this discovery revolutionized the field of particle physics, and since it was the papers were published in the same volume of PRL, therefore this particle we know by the name J by psi. And after this particle, many more, those we have discussed in this class, D plus meson, D0 meson, D0 bar meson, D minus meson, etc. There were many charm contained particles were observed in the experiments, but this one was the first. And then after charm, we had the discovery of tau lepton, and that again, if a lepton is there, tau lepton, then that means there must be a neutrino associated with that, and then that means there are 6 leptons. First generation nu e electron, second generation nu mu muon, third generation nu tau and tau on. 6 leptons and only 4 quarks. Then what happened? People observed another particle that we will discuss in this class, and that could be explained only when we have a new quark, and that was the bottom quark. And then to have the symmetry, which is known by the name Glashow symmetry, as many leptons as the quarks we have, or as many quarks as the leptons we have, therefore 6 quarks and 6 leptons. Therefore, in 70s, a new quark was hypothesized, and that was the top quark, which was discovered much later. But people thought that if there are 6 leptons, then there should be 6 quarks. Therefore, the important point is that this GIM mechanism was the driving force in the field of particle physics, because after that we had many discovery of new baryons and new mesons containing this charm and bottom, etc. And then that also in the 70s led to the rapid development of accelerator physics worldwide. Now, to understand GIM mechanism, let us go back a little in history and talk about first the protons and neutrons, which we have discussed in the class, that they form an isotopic spin doublet, and that we call by the name nucleon. Therefore, we call, because when you switch off the electromagnetic interaction, there is no way to distinguish between a proton and a neutron. Therefore, we call it by the name nucleon, and whose member are proton and neutron. Now, if you recall, we had introduced the isotopic spin operators, which were introduced in parallel to the poly spin operators, sigma 1, sigma 2, and sigma 3. Here we have tau 1, tau 2, and tau 3, and using them we can form raising and lowering operators. It will get clear very soon why I am calling it as raising operator and lowering operator. This raising operator is tau plus, which is tau 1 plus I tau 2 upon 2. And you see that this is simple algebra. Just I am putting the value of tau 1 and tau 2. This matrix is 0, 1, 0, 0, while tau minus is 0, 0, 1, 0. Then this tau 3 you can obtain from this commutator. Tau plus tau minus commutator is nothing but 2 tau 3. That means tau plus tau minus are related to this fellow tau 3. Therefore, we have tau plus, tau minus, and tau 3. We have to remember this, that these are related. They are not independent. Okay, tau 3 is not independent to tau plus and tau minus. But we have to remember this, that tau plus presently we are giving a name, that this is a raising operator, and this matrix is represented by 0, 1, 0, 0, while this is 0, 0, 1, 0. Now let us look back at this. N bar tau plus n. Since n is Pn, therefore n bar will be P bar n bar, a row matrix. Then we have tau plus as 0, 1, 0, 0. This is the column matrix, and this will give us P bar n. That means n is getting converted into P. A neutron, which is a charge 0, is getting converted into a proton, which is charge plus 1. Therefore, this is how you are raising the charge from the 0 charge to plus 1 charge, and that is why you are calling it by the name raising operator. And then similarly we have the lowering operator, n bar tau minus n. This will give you n bar p, and then a p is getting converted into n, and that means a plus 1 charge is getting converted into a 0 charge particle, and that means charge is getting lowered, and that is why tau minus is called a lowering operator. Now, keeping this basis into account, what we know, that in the doublet we had proton and neutron. Now similarly we had the quark doublet, SU2 quark doublet, where we had U and D quark. Now in this case we have Q bar tau plus Q, and if we have Q bar tau plus Q, then this we can write it as U bar D, and Q bar tau minus Q, that is equal to D bar U. Now here notice U is 2 by 3 charge particle, D is minus 1 by 3 charge particle. Therefore, you are going from minus 1 by 3 to plus 2 by 3. you are raising the charge, therefore this is a raising operator. In the second case, from 2 by 3 you are going to minus 1 by 3, and that means you are lowering the charge, and that is why tau minus is the lowering operator. Therefore we have q bar tau plus q as u bar d and q bar tau minus q as d bar u. Now we look at this case, beta decay process. N is getting converted into proton plus electron plus antineutrino, and that means simply a D is getting converted into U. You see, this is what we are talking about. A D is getting converted into U, or you can take an example where U is getting converted into D. So therefore at the quark level, the beta minus decay process is understood as the conversion of D quark to a U quark through the emission of W minus. Therefore you have a D quark that is getting converted into a U quark by emitting a W minus. Or if you have a beta plus process, that means a proton is getting converted into a neutron plus positron plus neutrino. Here a UUD quark, and here this is UDD. U is getting converted into D, then that means U will emit a W plus and will get converted into a D quark. The vortex we are representing it by GUD. Remember, this GUD is nothing but from Cabibbo. This is GW cosine theta. Now this is what the example we discussed. A proton is getting converted into a neutron, and this is possible again by the exchange of a W particle. Now the weak interactions in the charge current sector involve a pair of leptons from the same generation. Remember, for the leptons we have to conserve electron-lepton number or muon-lepton number or tauon-lepton number. Therefore we have to be careful that if an electron at some vortex is involved, then if this is a weak interaction vortex, we have to, if we want to have a neutrino, then the neutrino will be of the same kind as that of electron. Now even if I want to have a positron, suppose an electron is coming and here we have a positron, and we are talking about electron-positron scattering via a weak interaction, then that means this is possible through a Z0 exchange. And then here we will have an electron, and here we will have an outgoing positron. You remember, this is the incoming electron with electron-lepton number +1. This is an outgoing electron with electron-lepton number +1. Charge that is arriving at the junction is -1. Charge leaving from the junction, because this is the zero charge, therefore charge leaving from this junction is -1. Similarly, you have the electron-lepton number is -1. Charge that is arriving is this junction is +1. Positron is leaving, therefore electron-lepton is -1, and charge leaving from this junction is +1. Therefore, not only we are talking about neutrino, but at the same example, if we have electron-positron scattering, we will have a Z0 exchange. But if we have electron-neutrino scattering, then electron is emitting a W plus, or it should be W minus, and that W minus is getting absorbed by neutrino, and we have an electron here. Therefore electron-lepton number is +1 for this, +1 for that, and total charge arriving at this junction is -1. Total charge leaving from this junction is -1, is going out, and neutrino is neutral. That -1 get absorbed by neutrino, which is a zero charge particle, and in the final state we have a -1 charge particle, that is nothing but an electron. But we have to mind it that here we have to have the lepton of the same flavor. Similarly, we can think of muon, this example, or we can have a neutrino that emits a W plus and gets converted into a muon. Therefore, all the time this has to be of the same flavor. It cannot be a nu E and a muon, because we are not conserving lepton number. Therefore, the important point is that the weak interaction in the charge current sector involve a pair of leptons from the same generation or quarks. Such pairs can be regarded as the doublets. Therefore, we had 4 leptons. Therefore, this is the weak isotopic spin doublet. This is not the doublet that we talked about when we were discussing about the proton and neutron as the isotopic. They were the doublets when we were considering the strong interaction, because that was introduced when we are saying that we are switching off the electromagnetic interaction and there is no way to distinguish between a proton and a neutron, or there is no way to distinguish between a pi plus and a pi minus. Therefore, here we are talking about weak interaction, particles which are participating in the weak interactions, and we are talking about the weak interaction doublet or weak doublet. And the 3 quarks that we have, initially we had U, D and S, but suddenly after this kaon decay and the lambda decay, Cabibbo introduced the concept of mixing, and instead of UD we had UD prime, and this D prime was D cosine theta C plus S sine theta C. This we have to keep in mind, because we want to explain simultaneously the lambda decaying into proton plus electron plus antineutrino, as well as a neutron decaying into proton plus electron plus antineutrino. Now, the rates for neutron decay, as we have discussed, or the muon decay, found to be consistent with the inferred value of theta C. That is the most important concept, that if you have that theta C besides the mass part, the results would agree. And then with this sine theta C, you can understand the decay rate for lambda as well as for the kaons. And when you compare it with the case where you have neutron decay or pion decay, then we say that this where you have U to D transition or D to U transition, those are favored than where the case where you have U to S transition or S to U transition. And U to S or S to U transition, we call it by the name Cabibbo suppressed processes, and here we call it as Cabibbo allowed or Cabibbo favored process. Therefore, if we have Cabibbo favored process, then we have a cos theta C at the vortex, and if we have Cabibbo suppressed process at the vortex, we have sin theta C. But at the same time, mind it, electron neutrino vortex, muon neutrino vortex, both the places, they will have the same strength GW. Only the change in strength will be at the other vortex. Therefore, mind it, if I am talking about these 2 processes, a neutron is getting converted into proton. Therefore, neutron is du quark, and it is converting into ud quark, and this is possible when it emits a W minus. This W minus is giving me E minus nu E bar. Here also W minus is giving me E minus nu E bar when S quark is getting converted into a U quark, and here we have UDU, and this is UDS, a lambda. Therefore, this vortex will remain the same, GW at each point. But this guy, this is GW cosine theta C, while this guy is GW sine theta C. Therefore, while calculating the decay rate or scattering process, we have to keep in mind that the vortex at the leptonic side, this is not going to change. This will remain as GW. What is going to change is the vortex at the quark side, where we will have cos theta C if it is Cabibbo favored. That means it is the transition between the same generation, and if it will be sin theta C if we have the transition from one generation to another generation. Let us stop here. We will start discussing about the GIM mechanism in the next lecture. Thank you very much.